All right. Yesterday we talked about the contents of the course, and we finished the section, the chapter 5.2 on dipole moment and polarizability. Okay, and we started with the Virial Theory, and I'd like to continue there. Let me scroll down. In particular, we considered the time-independent Schrödinger equation with our usual Hermitian operator, the Hamiltonian, an eigenvalue equation. So you get the same function, and in front of the right-hand side as an eigenvalue, you get the the energy. Now it turns out, by simply exploiting the Hermitian property of the Hamiltonian, that if you have another operator, A, you can consider the expectation value of the commutator between the Hamiltonian and the operator. And if you do that, you will find, as shown here, that because the Hamiltonian is Hermitian, because it's a hero, we find that the expectation value of this commutator must be 0. Okay. And so this is what's stated here, right? This is also known as the Hyperviria Theory. All right. And in order to arrive at the Virial Theorem, we now need to consider particular operator A, right? So the Hyperviria Theorem is in general, and the Virial Theorem is about a particular operator A, namely the sum over the product of positions and momenta. All right. Now, in quantum mechanics, your momentum operator is minus I h bar derivative with respect to spatial dislocation. So our our positional variable is Q. So that's the derivative with respect to Q. Right? So it's a first order differential operator. Now you know that differential operators are linear. So it meets the condition to be linear as shown above. And it's only dependent on the position. So it also is time independent. Now let me get my notes. Now, this is also not an uncommon quantity to consider if you just think about Heisenberg's uncertainty relationship. It's the product of positional variance and momentum variance that is bound, right? So compare to Heisenberg's uncertainty relation, right? So it's not as if this was some crazy object to consider now. All right. So what happens if we consider this now? So we write down our commutator. So in this case, our commutator would be the sum of H commuting with Qi and Pi. Okay. Now, when you have a commutator that contains as an argument a product of two functions, there's a commutator rule. So let me show you this, which you should know, but just as a reminder. So if you have two operators, A and the operator of the sequential application of B and C, then that is nothing else than A, B commuting and then applying C, or first applying C and then the commutator, plus first the commutator of A and C, and then applying B. All right. Okay, so that's the simple commutator rule. And if we apply that in this case, we would hence get HQ B plus Q HP. The whole thing in brackets. Now, also from introductory quantum chemistry, you should know the commutators of H with Q as well as with P. So just as a reminder, these are known. The commutator of H with Q is nothing else than minus I H bar M P. And the commutator of H with P is IH dq of the potential that's in the Hamiltonian. So if you insert this, then you will find that our expression becomes the sum over I minus I H bar. Now we have to pay attention. Unfortunately, I use I as an index for the particles, and you also have the imaginary number I, okay? So please be careful here. So let me maybe specify this here as well. Just so we're on the safe side. 1 over mi. And now we have, from the commutator, we have the P, and then from the commutator rule, we have another P, so that's Pi squared plus I H bar Qi derivative of V with respect to Qi. Now, if you look long enough at this, you will realize that the sum over the momenta is just your kinetic energy. So this is minus I h bar 2 times kinetic energy plus I h bar. And now we have the sum for Qi derivative Qiv. Okay. So let me keep the operator symbol to denote that we are just considering the commutator here, not yet the expectation value. Now, we can insert this in our expectation values. And so in the Hyperviria theorem, so we know that 0 equals psi HA. And now we know the expression for that commutator, so we just insert it here. Psi minus I h bar 2t plus I h bar sum over Qi IV psi. Okay. So the prefactors, this I h bar and the IH, and the IH bar in front of the potential term, these two guys cancel, right? And if we then arrange, we see that 2 times your expectation energy, your expectation value of the kinetic energy operator. So this is the kinetic energy, right? This thing 2 times must be equal the sum over Qi dQv. Okay. Now, if you consider this this derivative here, right? There's a potential derived with respect to distance, right, or to spatial. Right? And this is what we commonly call a force, right? So this is a force. Excuse me, I should put the operator symbol. So this is a force term, and this is what is known as the Virial Theorem. Where the word virus is Latin for force. Now, this is really, it really holds in the, so one condition for this theorem to hold is that your wave function psi must be it cannot be a trial wave function, it must be the true wave function. So if you plug in a trial wave function, then this equation only holds approximately, right? So this is exactly true if and only if psi is true wave function. So you could imagine, for instance, that with an approximate wave function, the kinetic, the error you make on your kinetic energy term is different from the error you make on the right hand, the force term, right? And then these two guys would not be exactly equal. So psi should be the true wave function of bound electrons, right? Now, this expression is certainly interesting, right? You can differentiate your potential, but it's a bit tricky because this potential operator could be tricky to obtain or to evaluate, right? And so there is something we can do to go beyond that. So that's sort of the third step, right? The first was the Hyperviria, very generic theorem, which is valid for really any hero with any linear other operator. The second step was that we obtained this Virial theorem, and now we can do a third step, right? So if you wish, we can call this A, and then we call this here B. And now we can do something else, and this is under a certain condition, right? So if you have this form, x times dx of some function of x, right? Whenever you have this kind of situation, variable times the derivative with respect to that same variable, right? What you should be thinking about is Euler's theory, okay? Now, Euler is, of course, a giant in the sciences. He happened to study in Basel, just like you. And he introduced this theorem, namely that if, so this can become n times f of x if and only if f is a homogeneous function of nth degree. Okay. Now, what does that mean? So, a homogeneous function is a function which has a property that you can have prefactors in front of your variables, and you are able to pull them out in front of the function. Okay, so you can basically factor out something. Okay, and this something should be some other variable, some other number with a power of n, right? With a degree. So we'll specify that in a minute. This condition. But if that is true, right? So if this is true, if and only if, right? If and only if, then we can exploit this. So in particular, if our v, so that's our function, is homogeneous degree n, right? Then you can replace sum over q I dqi v by n times v. Right? So that's pretty awesome. Right? So your entire sum of all these degrees of freedom was has vanished, right? And you're left with just v. Now, if that's true, right, what happens to your Virial theorem? Well, you just substitute it, right? So your 2t equals n times v, right? So this is known as, so this should be C. This is the Virial theorem for homogeneous potentials. And it turns out it's actually, if your potential is homogeneous, it's only true in the potential energy minimum. So in the minimum of a geometry, right? Holds for geometry minimum. So if we then assume, and typically that's okay, right? That energy is conserved, right? So the unperturbed, if you don't have friction terms or interactions with environments and so on, your total energy, so using conserved energy, E tot is T plus V, right? So you combine these two and you know the rule that your potential energy contribution is 2 times n plus 2 E tot. So you have eliminated the kinetic energy. And likewise, you can eliminate the potential energy. So your kinetic part would be then n over n plus 2 E tot. Okay? So this is what the Virial theorem implies if the potential is homogeneous, right? Now, this can be extremely helpful because it turns out, for instance, if you use what is known as density functional theory, right, which is a theory built, and we will discuss this later. It's a theory built on using the electron density rather than individual electrons, right? Then we do not know the kinetic operator that helps us to, that allows us to calculate the kinetic energy. Okay. So this means if you have now this additional relationship from the Virial theorem, you can eliminate the kinetic operator, and you actually don't need to explicitly know it, right? So knowledge about operators is something very precious, right? So the correspondence principle, which is sort of introduced, often it's not remarked on its fundamental importance. This correspondence principle is not always available to us, right? So we don't have the correspondence principle for the kinetic operator in terms of an electron density. expression of eigen expectation values. And so any such relations can prove tremendously valuable. All right. Furthermore, of course, this is extremely helpful also to simplify the expression such that bonding becomes amenable to intuitive understanding, right? So, we will see this in the next subsection where we discuss the chemical bond. Right? You will be able to understand chemical bonding in very easy terms, which are 100% rigorous and reliable and rooted in quantum mechanics, following the derivation which we just did. Okay, so that's the second important consequence of this. Now, before we go there, though, we should really discuss how do we know if something is a homogeneous function, right? Because only then we can make use of this nice Virial theorem for homogeneous potentials. All right, so basically this is Euler, who there's a function a homogeneous function f of degree n obeys that f in some variables s x1, s x2, s x3, and so on until your last variable xj must be the same, right? These are all variables. This must be the same as you pull out your s in front of f and you raise it to the power of n. That's the degree. The s doesn't matter. It's just a prefactor. Okay, can be just can be anything. And f x1, x2, x3, xj. Okay. So that is basically the condition. Right? If that equality holds, right, then you're dealing with a homogeneous function of degree n. And if your potential holds for such a relation, then you're dealing with a homogeneous potential, and this nice simple relation above follows. So here's an example. One. F should be 1 over y cubed plus x y square z square. Now, is this f a homogeneous function? Let me clarify this a little bit more. So f is a function in x, y, and z. Okay, is it homogeneous? Yes, it is homogeneous, and it is homogeneous of degree 3. So you can see this. If you use f of Sx, Sy, Sc, then you have 1 over S3, Y3 plus Sx over S squared, Y squared, S squared, Z squared, right? And so that is the same as S to the minus 3 F of X, Y, and S. Right, so you can factor out the S. In the second term, the S in the numerator cancels with one of the S's in the denominator. And so you have exactly your F with the prefactor S to the minus 3 in front of it. Example 2. Is f of x equals x to the n. Homogeneous? Well, that's easy to test. S to the power, so s times x to the n is s to the n, x to the n. And so you would find that this is homogeneous, right, of degree n. So n can also be a variable, right? Now let's use Euler's theorem then for this, so we can easily see this. X times dxf is x times n times x to the n minus 1, right? And that is then the same as saying n times x to the n. So that is n times f. There's a question in the chat. Is n equals j? No, n is not j. No, not in general. Yeah. I mean, let us know if you have more questions, right? But, so j was in this example here, or in this spelling this out. It's just the index over the number of your variables. Right? It's not always obvious what is a variable and what not, right? So here, for instance, f could be also a function of other variables. I don't know, whatever. Say z1, z2, and so on, right? Until zj, doesn't matter, right? But for the relationship with respect to x, right, you only need the function to be homogeneous in the variable you care about, namely the one which you want for this relationship, right? So the gradient in x, that's the force that matters, right? Not all the other variables. You can consider them to be constant. They don't depend on x, right? You don't need homogeneity in all degrees of freedom of the function, but just in those you care about, right? All right. So let's consider 3 examples now. From chemistry. or relevant to chemistry, right? The first example would be the 1D quantum harmonic oscillator. Okay? So your V, your potential, is equals 1/2 kx squared, quadratic potential of the harmonic oscillator. Now, is this a homogeneous function? Yes, for n equals 2, you find 1/2 k sx squared equals s squared 1/2 kx squared is s squared v. So yes, it is a homogeneous potential, right? And hence we can use our Virial theorem. So 2t is the same as 2v, right? So the 2 cancels. And then the whole thing must be, so E tot equals t plus v equals to v. So v equals 1/2 E tot. Now we know E tot for the harmonic oscillator is h nu n plus 1/2. Now this n is your quantum number. It's not your degree, okay? And if I substitute this, this means the potential energy in my quantum harmonic oscillator is always half of what the total energy is. So half h nu n plus 1/2. Okay. So you have a rapid, immediate access to knowing how the total energy is partitioned into potential and kinetic energy. Okay. Now, note also, right? Remember the probability discussion with Born's rule in the second chapter, right? There's all this this sort of reference to quantum mechanics, claiming that we cannot know what matter is and in which state it is, and it is outside the human's grasp to fully understand how matter is composed, right? In some sense, that's true, of course, but in some other sense, we do have a very detailed understanding. For instance, even the partitioning of potential versus kinetic energy, just as in a classical system, right? We can, thanks to the Virial theory, and as shown to you now, we can, on pen and paper, you can understand that, right? So it's a very misrepresenting view if you claim that due to quantum mechanics we don't know anything or we cannot know anything. That's not true, right? So we know quite a lot, right? So let me go to the second example, the hydrogen atom, right? That's maybe, you might wonder, okay, quantum harmonic oscillator, that's the a theoretical concept. But what about the hydrogen atom? Well, here the nuclear charge is equals 1, right? So 1 proton and 1 electron, right? We also know the total energy to be minus 1/2 Hartree, right? That's for the hydrogen atom. Now, how does the potential look like? The potential in space, right? It's a spherical problem, right? So that's simply 1 over the distance to the atom, right? So that's easy. Now what is this distance? We just use Pythagoras, right? So x squared plus y squared plus c squared. And we have to take the square root, okay? So this means then if you, is this homogeneous function? Yes, it is, right? And the n is -1, so degree -1, right? That's easy to see. We just, and that is something that could come up in an exam situation, right? Show that this or that potential is homogeneous. Right? So then we simply plug the S in front of every variable. And that is S squared times x squared plus y squared plus c squared, square root 1. Now hopefully you see it already. And this is -1 over S, 1 over R. Okay. So the relationship, the degree is -1. So this means 2 times the kinetic energy is minus V. And this is, if you just contrast this, right, to the harmonic oscillator. So you have a change of sign, right? That's as different as things can be in physics, right? Now, where does it come from, right? It comes from the shape of your potential, right? In the case of the harmonic oscillator, your potential looks like this. In the case of the hydrogen atom, it looks like this, right? So very, very different sign, opposite sign. It's not because the potential of the hydrogen atom is negative, right? That doesn't matter for the degree. What matters for the degree is that it's in the denominator. So your polynomial, your inverse polynomial potential, right? This kind of curvature. That is really that push that thing in, right? And you immediately see that now the kinetic energy has opposite sign. So kinetic energy is repulsive. Yeah? So we can now use our rule that V equals 2 minus 1 plus 2 E dot, right? And that means we have 2 times E dot, right? Minus 2 times 1/2 is 1 minus 1 Hartree. potential energy in your hydrogen atom is -1 Hartree, and the kinetic energy then must be +1 Hartree. Okay. Okay, I have a third example. We look at this tomorrow, where we will extend this to any atom, not just the hydrogen atom. Think about it. You could check if it's homogeneous. It turns out it is. We get a slightly, no, sorry, we get the same Virial theorem. It also has the degree of -1. This holds for any atom, right? Actually, for any atom. All right, we've passed the hour. Let's stop here. As always, for any questions, please let us know, right? You can also talk to Mr. Trestman. And I'd like to thank you for your attention, and I wish you still a good end of the week. Bye-bye.